Okay, awesome. So in this session, the first talk is by Thomas, and he's going to talk about his work at Oraclize.
Hello to everyone. Thank you for having me here today. So during this presentation, I will try to explain some of the concepts around trusted execution environments and trusted computing in general. And I know that there are a lot of smart people in this space that are trying to figure out how to solve complex off-chain problems via incentive mechanisms or via new crypto techniques. We are probably not that smart, so we choose instead to leverage like trusted computing technologies in a way which is very different compared to what the other groups in this space are doing, and hopefully the work we are doing will be useful for the entire ecosystem. So all the work I will be talking about the generalization of trusted computing is open source, and we hope that other groups will start contributing to it as well. So this is where we started. We tried to understand how to overcome the walled garden limitation, and we started from like the Wikipedia page written in 2011 or something. Sorry, not Wikipedia, the bitcoin.it wiki page on oracles. And when we started, the concept of oracles was really not much developed. Ethereum and other blockchains were not there yet. So we had to do some of the heavy lifting. Now there are many groups working on oracles that have benefited from our work and that are continuing to like improve this space. So the idea is like, how can we verify external conditions in a way which doesn't compromise the security model of the blockchain? Like, let's say that we have an application on the blockchain. It may be a simple payment. It may be a smart contract, anything really, which wants to check some external conditions, such as the temperature in Berlin or something like that. This is complex because blockchain platforms like are isolated. So we say that blockchain applications live like in a walled garden, and that you cannot really reach out to any external context because it will be very complex to make it fit with the consensus, right? With a global consensus. So we started by trying to define those three base components. So let's start with the naming, indeed, and let's try to agree on this. So this is very general purpose. So the oracle, of course, it's not necessarily us. It can be any oracle. So the oracle is this concept of like the provider of data to the application. The application can be a blockchain, an application on the blockchain, or it can be anything, really. It doesn't need to be an application blockchain related. While the data source is the provider of the data. So let's make an example for making this more concrete. So we may have like a smart contract on Ethereum that wants to check what's the temperature in Berlin according to Wolfram Alpha. So in that case, you would have like the application being the smart contract, the oracle being whoever talks to the smart contract and the data source, and the data source will be Wolfram Alpha itself. So in that case, we are trusting the data source. And if you think about it, external data, which lives outside of the blockchain, most of the times, if not always, is trusted. So if I ask you, like, what's the temperature in Berlin, you would need to make many assumptions. Like what's the unit I expect, how many decimal places I want, where exactly in Berlin to get the data from, and also I will need to trust, the physical sensor not to be tampered with. So there are many possible attack vectors, and the oracle is the interesting part. Like, how do we make an oracle which is trustless, or how do we minimize the trust to a level where it is acceptable in the blockchain space? Because as for the data source, the solution is pretty trivial. It's the one of not just choosing one, but choosing many and saying like, okay, fine, I get the temperature from like 10 independent ones, and I try to aggregate it in a way that makes sense. But in general, we don't expect like the majority of data sources to adapt to the blockchain because, well, for different reasons. First, because this is not their focus. They just want to provide data. And the other is that, there are many blockchain platforms. So Oraclize is trying to generate some kind of guarantees about the secure connection with those external data sources. How do we do it? Well, ironically, we are a new kind of intermediary in a sector which is trying to get rid of them. So why would you trust an intermediary like this? It doesn't make any sense. We are trying to disintermediate, and we propose a new intermediary. Well, our opinion is that this is crucial for like the ecosystem to work. We don't expect there to just be one operator running the service, so we expect other people at some point to run a similar services. But as you will see shortly, the only issue to have this intermediary is that the system may not be available for some time, but we are trying to give a strong guarantee on the fact that the data we send to the blockchain is authentic. So it's the same as the one reported by the remote data source. So right now we have integrations with those blockchain. The one on Bitcoin is quite complex, and it's not the like subject of this talk. We are also reiterating on it because we were making heavy use of like some opcodes that apparently are not going to stay there for much longer, like the code separator and the alt stack and things like this. So yeah, it was a nice experiment on Bitcoin, but we are now trying to understand how to integrate with upper layers in a way that makes sense, so that we can get conditional like payment channels, so that we can make some payments that depend on external conditions. So let's dive for a little bit into the authenticity proof, which is really where most of our work is. So as you will see in the presentation, all this is really blockchain agnostic. It doesn't have much to do with the blockchain, but it can help a lot in the blockchain context to secure some critical processes that you may need off-chain. So we have seen also in previous presentations that there are some open challenges to monitor the channels, to monitor the blockchain, to understand what to do. There are many other challenges in the blockchain space that we will have in the coming years. And we have tried here to design something which can be more flexible and more secure than using Intel SGX, as many groups are proposing. So let's try to dive into it. The concept is this. So basically, we want to authenticate the data coming from an external party. And this external party, namely the data source, could be anything. So it could be a web API, as in most cases, like I want to check data coming from that specific web API. But it could be also a piece of code. So the data source is very general purpose, it's very wide in scope. It can be anything. So any provider of data is considered the data source. So how do we authenticate something like that? Well, one very flexible way, not to have too many restrictions, is the use of trusted computing. This is not the only way, because when we started, we were using TLS Notary, which was a protocol designed for Bitcoin marketplaces a few years ago. They wanted to give some guarantees on the fact that a wire transfer was really sent in exchange of Bitcoins, and TLS Notary enables the auditability of a TLS connection. And page signer, really, not just TLS Notary. But unfortunately, TLS Notary and page signer, which is this simplified implementation, let's say, it needs you to trust Amazon for the way it works, because there is a component which you assume trusted, which runs on Amazon Web Service machines. So you're really trusting someone, and this is Amazon. Unfortunately, another limitation of TLS Notary is that it works up to TLS 1.1, which will be deprecated starting tomorrow, I guess, or something like that, by end of this month. So it's not really compatible with future versions for the way it works. So it was a very nice trick invented by Adam Gibson and others a few years ago. So we try to understand what made TLS Notary interesting and page signer interesting. And really, the ultimate answer is that you have to trust someone, which is Amazon. So it's not worth diving too much into a system like this if you use it alone with no other additional component. So we started looking at Intel SGX as well. If you are not aware of the work of Intel SGX, I think there is another talk or two about it. Unfortunately, I'm quite disappointed about this. I hope this will change, but I know that in the last year and a half, all people in this space, all the different groups having a security problem, like we don't know how to solve this, they're just using Intel SGX, saying, okay, fine, we have the solution to the problem. We don't know how to create a safer system, so let's just use Intel SGX because it's good enough. And it's basically just a sandboxing technique, which uses like recent Intel CPUs to execute a process in a way which is impossible to tamper, according to Intel. Why? Because I bet that most of you don't have the capabilities at home to verify that your Intel CPU doesn't have a backdoor, and you don't have the schematics to check it, and you don't know if all the CPUs like this have the same issue, and you're also relying, at the moment at least, on an attestation service, so like an external service that helps to verify that the system integrity is fine, which is run by Intel. So at the end of the day, for different components, these are just some, you are trusting Intel. And if you think about it, any isolation techniques, any security module is implemented by a company. And you will never be able to verify everything independently. Because if it relies on hardware, it's basically impossible and not scalable, to verify every single chip, and you will most of the times miss the basic components to be able to verify it anyway. So the interesting part here, in my opinion, is that you have to understand that each one of those technologies, here you find others, that provide similar security or similar functionalities, they are provided by a company that you have to trust in a way or the other. So with Intel SGX, of course, you are minimizing the trust, but you are still trusting Intel. If you use like the Ledger Nano S, I guess that most of you know what it is. It's like a hardware wallet in the blockchain space. Why is it interesting compared to all the other hardware wallets? Maybe you didn't know that, but on the Ledger Nano S, you can run custom applications, and it has attestation capabilities. So you can get a signature from Ledger claiming that a given application running on the device is running in a safe environment according to their best knowledge. So again, you are trusting Ledger in that case, but you are using a different architecture, and you are trusting a different attestator. So here, basically, you have a critical process that you can run on Ledger Nano S or on Intel SGX or on alternatives like on trusted execution environments from Qualcomm or on an Amazon service via page signer alterations, or like on Samsung Knox or other things, where you're trusting someone else. Why is it interesting? Well, because if you leverage one of those, you are compromising, you are giving up the security model of the blockchain to a single player. So why do we even discuss about scaling up the blockchain if you then want to trust a single player? Well, in that case, just ask them to run a single node and you have the same model. It doesn't make any sense. So the approach that Oraclize follows is the one of saying, fine, let's not leverage one because this is very limited and it's not really interesting. Let's try to minimize the trust for real by using all of them at the same time to secure the same claim. It's like if you want a multi-signature of trusted computing elements. And this enables, well, first of all, you can quantify approximately the cost to compromise that system. Because if you look at Intel SGX, well, the cost is, I don't know, it's close to probably some tens of thousands of dollars to break it, because it's very new, and in the last year there was one paper every 2 weeks explaining how to break it in a different way. So it's really not that safe by itself because it's new. But if you put all of them together, you will need to break a claim to have all these different attestators to cooperate and to basically be broken at the same time in a coordinated fashion, which is it's more unlikely at least. So why are we doing this instead of asking to those attestators, to those companies to come together in a consortium? So I often, people last year were saying that 2018 was the year of consortiums, of consortia, because there were one consortium every month or something. So people expected those companies to come together and start an Oracle consortium or something. Well, first of all, the word Oracle is not something you can use, apparently, because Oracle Inc. is like sending letters to all people working in this space, saying that Oracle is a word in the dictionary that they own. So don't do that. But second, even if they were named differently, you would have many problems because if they come together in a consortium, it's an explicit agreement for a cooperation. So it basically lowers the trust in the system and the security in the system because you have those people that are willing to cooperate and they are already together and even if they are competing, they would have an easier time compromise this security model. So this is an example in Solidity why you could use it. You could use this without blockchain via HTTP API to generate the authenticity proof. But most of people are using it on Ethereum because it's easy to do it right now. Again, our efforts are 90% blockchain agnostic, so this is just one way to use it. And you just specify what you want, like in this case, it's a URL, so you just want to do an API call, and you want Oraclize to send back the result without tampering it. So you select the trust model. Here the trust model is like, I want the proof to be generated via TLS notary. You could potentially choose other players, all of them, or whatever. And then Oraclize sends it back. And in this case, you have this weird intermediary that is Oraclize that basically generates a signature, but not a signature done by Oraclize itself. It basically generates a signature. It asks to the external player to generate a signature. So you have an external guarantee that claims that the intermediary is not cheating, according to them. What you get is those authenticity proofs, which is, the format is slightly different depending on the technology you use. We have unified the format with something called Proof Shield, which is a concept on which we have been working on for the last 6 months approximately. And this is basically just a technique to leverage the same trust line with the same attestator to simplify the proof and making it much smaller. So this enables the proof to be verifiable at a small cost on blockchains, for example, or it can be used to have compatibility with other legacy systems, or even with Bitcoin, it actually could enable few things because you have a proof which is really short and verifying it is just very few steps. And it is also attestator agnostic. So this is a unique format regardless of the technology you are using to secure it. So this is quite interesting. Well, here I had something about randomness, but I will skip it because I've seen that there are other talks talking specifically about randomness. But one of our use cases well, we are trying not to define them ourselves, right? We are trying people to build on the top of this technology. But apparently, one of the few use cases that Bitcoin blockchain is really has proven to be useful for right now, other than store of value and maybe payments in the future, is gambling. So hopefully in the future, a few other use cases will be enabled. But right now, it's mostly bullshit. So this is auditable off-chain computation, basically, and it's a way to keep the flexibility of the traditional ecosystem, of the traditional cloud model or non-blockchain computation model, and saying, okay, fine, we don't need to decentralize everything. We need to make a system that makes sense. So let's keep the consensus layer there, and on the top of it, let's move. Let's get some guarantees on a computation. So why? Well, in some cases, you may not need this security model because maybe you have an incentive mechanism like on Lightning that makes sense. But in many cases, you need to get external help because maybe you need to get some guarantees on the fact that you're continuously monitoring something, or maybe because there is no solution yet, or there is no incentive model, or maybe because your use case is not huge, and you don't, bootstrapping a new incentive model and a new network is not trivial, as we see it on Lightning Network, for example, and others. So it makes sense to get, a trust-minimized system like this, which doesn't require you to bootstrap anything, and you can just generate the authenticity proofs for your process and know that, it's not 100% safe, but in order for it to be broken, you will need all these different companies to be compromised at the same time. So you have basically their reputation at stake. We have to keep in mind that we are not aiming for 100% security, not even on Bitcoin or on blockchain. I remember like this tweet a few days ago where people were talking about Gregory Maxwell, that a few years ago he was saying that the Bitcoin paper was bullshit because it's impossible, and he had proven it, to have a fully decentralized consensus. And that's true because Bitcoin is based on a statistical model. It's not saying that it's 100% that you always reach a 100% consensus in all cases. It just depends on some assumptions. It's based on some assumptions. So what are we doing? Basically, abstracting out the complexity of those systems, of those trusted computing techniques of different companies, not just on one, and well, putting all of them in a single box. Why? Because we expect that different groups will be interested to run something like this. And while on paper it's very easy to buy on the shelves those different components, in practice it's very complex, especially to configure them properly. So we are trying to create this system and those machines that in the future people will be able to use and to verify independently and to generate those kind of guarantees for themselves or to provide them as a service, for instance. So many times people ask, what's the comparison of this with Truebit? You can secure any computation. You can do it also with Truebit, right? Well, essentially, the trust model is very different, and also the constraints. So this system is very flexible because it doesn't need to be deterministic. It doesn't need anyone that wants to verify the computation to run it again. It just needs, it's not based on an incentive model. It's just based on the fact that the single execution of the process is correct according to a set of players which have something at stake and which are in competition. So again, it's trust-based but trust minimized. So right now, well, we have been live on mostly Ethereum. Now we have integrated also with Rootstock, Monax, R3 Corda, many things. But most of our clients use it on Ethereum right now to generate, to use smart contracts that depend on external data or to delegate off-chain computations. What we have seen, and what everyone probably has noticed as well, is that writing smart contracts is not trivial, even if Solidity looks easy. Namely, writing complex applications is, takes time, and the attack surface is huge, and the cost can be very high. So this is why the smart contracts in production on the Ethereum mainnet, if you want to call it production, yeah, they are relatively small. Like they are gambling games, conditional payments, like if the flight is late, then pay out. Or they are, ICOs, or they need some price fees. Maybe they are doing some, checks on a given price, condition, or simple financial instruments, things like this, parametric things. So we have basically tried to understand if this security model could be useful also on upper layers. And we are right now doing some research mostly on Raiden and Lightning Network to understand, if this could be useful to enable like additional guarantees on upper layers, other than on the base blockchain layer, as it is already doing now. And apparently, there are some things that make sense. One that we have just pushed out in the wild to see if anybody's interested to use it is a system where you define a function in Solidity, which can be anything, and then you delegate to this off-chain context the computation of the result. So the system basically generates within these safe boundaries, provably safe boundaries, to the system, you generate the result and you send it back on-chain. So there are many ways to do it. This is one. The interesting part here is that you can verify it on-chain at a constant cost. So regardless of the complexity of the function you want to delegate off-chain, you can get it at a fixed cost. And if the verification doesn't pass, you can fall back to on-chain execution. So it means that you can optimize the costs in the best case. Yeah, you can use it for many things, like to verify payments on Bitcoin. You can just keep a node on these boundaries for Bitcoin, just check the payments. You can do anything because you have complete flexibility. So again, it's not 100% safe, but you can easily quantify the cost to break it, and you have complete flexibility. So having smart payment channel is something we are actively investigating, and that's, yeah. It will probably still take some time, mostly because it's those Lightning Network and Raiden are still quite at an early stage. So they are in production now, but it will take some time to solve problems. And we have already built on Bitcoin too early, and now we have to write everything from scratch. So we just want to wait for some more time. We are also trying to make the description of the computation different, so that you can describe it differently. Right now we use Docker just because it's a very standard way to describe the context. We don't use it for isolation because it has proven in the past to do it really bad. But we just use it to describe the context, like you describe the computation. You may have heard of the Moxie virtual CPU or WebAssembly. So we are investigating those as well to integrate them as different ways. But yeah, this is most of the future work that we have in mind and the things that we are currently working on. Something coming out very shortly is having decentralized exchanges on Ethereum which secure the order book, the order matching via this guarantee. So the order matching typically is verified on chain in the sense that if you match two orders, they need to exist and you need to check something. But the operator of the order book that lives off chain can potentially cheat, and they could do front running. They could try to get the best orders for themselves and so on. Via this system, you can very easily try to check that this is not true. This is not happening. That's mostly it. So yeah, this is probably this is the result of our works in the last couple of years. So we are getting some traction, and we are doing a lot of research and development, but we are also being used for real, which gives us a good motivation to keep the system as safe as possible, because right now there are tens of millions at stake or something. Yeah, that's it. Thank you very much.
Okay, Chang Yu, you're on fire. Here you go. Okay, this work. Yep.
Okay, so you said it's not 100% secure, but if things go wrong, will anybody be held accountable for that?
Basically, what we do is having the authenticity proofs signed by these external attestators and sending back on chain. Yeah. So anybody could verify at any time if we have ever provided a wrong answer or an answer where it was not, the proof was not passing in the last 3 years. And right now it has not happened, or we would have gone bankrupt. This is, it's just our reputation at stake, in the sense that our promise is the one of not sending on-chain proofs that don't pass, but smart contracts could potentially verify them before using them. So the reality is that if the smart contracts do the on-chain verification on Ethereum, for example, there shouldn't be anything happening. You should have a fail-safe mode or something. And the only thing that could happen is that the attestator signs something which is wrong. In that case, on paper, the reputation at stake is theirs and not ours.
Thank you for a talk. One question. How difficult is it to validate a proof? Are they big? So my idea is you talked about smart contracts. Is it difficult to create a contract, to create an output in Bitcoin, like I'll pay to someone if you'll provide the proof of some executed C++ program and so on?
Yeah, as I briefly mentioned, we did some work on Bitcoin that was kind of enabling this. But the transactions, the script turned out to be relatively big. So we don't see it as a scalable solution. And we have kept it just a prototype. So if you are interested, we can disclose our work. We will be happy to get some feedback. We did some presentation about this. But we didn't want to publish it too much because basically it's already outdated, since it is using code separator and alt stack and other things that probably don't have any reason to stay there in the medium term. So,
awesome. Thank you very much for that, Thomas. Awesome.